Oh my goodness. So who here is here as a first-time Stir Trek attendee? Oh wow, a lot of you. I can't believe they've had this conference for 10 years. 10 whole years. I've been here, I got to the Star Trek game kind of late. I've only been coming here about 3 years or 4 years now, I think. But I love this conference. I love that it's local to Columbus. I think that these guys put on a heck of a job doing this thing. And you're continuing to see evolutions in that. And I think the setup we have today and everything is fantastic. I mean, if you agree, go ahead and clap, because I think it's been great so far. And kind of one other thing I'll mention before I get going is there are a ton of people that go into making an event like this work. So if you see people today, like this gentleman in the orange shirt, anybody in an orange polo is a volunteer or an organizer. Plus the AV guys are working their butts off too. So if you see them today, like just take a couple minutes, tell them thanks. You know, they want your feedback, good or bad. So make sure you're communicating with them, tell them how much you appreciate all their hard work today, even if it's just somebody handing out coffee, like somebody's dedicating their time to making this event good. So please make sure you tell them thank you. And the other thing is there's a ton of sponsors out there, you know, sponsor dollars go a long way for helping put on an event like this too. So make sure you visit them, enter to win cool stuff, tell them thank you as well. So we'll get going here in just a few more minutes. Hopefully I can walk around here a little bit. That's pretty meta. If I took a picture of myself taking a picture, is that like dividing by 0? I don't know. Let's see. Yeah. My phone's actually going to make a feedback sound. There you go. Oh, man. So this thing's going to go about an hour. Sorry. I know some of the sessions got out a little earlier. There's a lot of stuff I want to talk about and a lot of stuff I want to show you. So if you're anxious to get out of here for lunch, I'll understand. Me, I'm going to get out of here and get a beer. Anybody's welcome to join me. Because, you know, it's almost beer o'clock. You guys enjoying yourself so far, though? I hope you guys are. A lot of good stuff today. You paid for your seat. You're only going to need the edge for this one. Talking about databases. Talking about databases. He talks about databases. You can sit up here with me if you want. There's a seat right there. I'm sure they won't mind. I'll just be walking in front of you a lot. All right, I've got 11, so I'm going to go ahead and get going. So everybody, welcome to Understanding SQL Server Execution Plans. My name's Drew, and I'm here today to talk about why execution plans matter, because at some point or another in your development career, whether you're an app dev, SQL dev, even a DBA, you're going to run into cases where you want to know why a query is performing a certain way. And through the use of execution plans, that helps you understand what's going on under the covers with SQL Server to help you either fix long-running queries or slow processes or write better stuff from the jump. There we go. So who am I, and why am I up here talking about execution plans? So I've been working with the Microsoft Data Platform for over 15 years now, and I love it. I love every part of it. It's been really good to me. I also enjoy really helping developers and new people to the platform understand how to write really efficient, really high-performing SQL, and also helping people tune stuff that isn't written like that. I work at IGS, which we're based there in Dublin. We have a booth outside today. I encourage you to stop by and say hey. We got all kinds of cool stuff to give away. If you want to reach out to me, there's a couple different ways to do that. I have a really burdensome last name with a lot of vowels. You're welcome to take a picture of that if you want. But it's really hard to spell, and it's even harder to say. So if you want to email me, I have some business cards. And what I'll do is I'll hang outside of Theater 27 when I get done here. So if you are in here or you're in one of the simulcast theaters, come over and see me. Would love to give you a card so you can communicate with me. If you like watching me make a fool out of myself on Twitter, I'm at Pittsburgh. For every 1 or 2 posts I make about SQL Server, I probably tweet pictures about my dog. So if you're into both of those things, win-win. I have a website, which is port1433.com. I could not believe that domain was available. If you go over there, I'll make a link posted on the StirTrek site later today where you can go and grab my code demos and my slides if you want them. And then finally, if you get bored during this presentation, which I hope doesn't happen, but if it does, I understand, pop on over to genesface.com. That's a website we maintain at IGS where we take pictures of my boss, Gene, without his permission. And he's a pretty good sport about it. We've only been called to HR a couple times. But otherwise, pretty good-looking man, so if I do say so myself. So go ahead and check that out, too, if you get bored. Other thing I want to mention is, outside of being a regular DBA, I also really enjoy using the data platform for kind of stupid goals. So we had an idea recently where we were going to try to put SQL Server in a weather balloon. And here is kind of a picture of our first attempt of a flight. What my very tall coworker is holding in the back there is a cooler that actually has a fully functional SQL instance in it. And the plan was to let that thing go up to about 100,000 some feet and collect data as we did it. Our first attempt didn't quite go the way we anticipated. It was not a good day for anybody, especially the guy that had to come and cut that off the power lines. But we went a second time, and we actually got some pretty cool footage of the entire thing. If you're interested in that, you can learn more about that over at port1433.com. There's an entire high-altitude SQL Server project section over there where you can read about it. And we are going to go for a third launch. Don't really know when. We had some challenges with our second flight, even though we managed to get it all the way up there. We're going to go again, and you can follow along on Twitter and at the website. Other thing I want to mention real quick, I'm sure you guys have seen this. Now we're in our third session of the day. There is a dedicated Slack set up for StirTrek today. And if you have questions that you want to ask during the session, you can go there and get them. I will say that I probably won't have time to take questions as I'm talking. But I will be checking the Slack after the session today and this weekend and next week. So if you drop questions in there, I'll get to them as soon as I can. You can also hit me up as a DM on that channel as well if you just want to get at me that way. It's still at PitFurg over on that channel as well. So make sure you go over there and join that. You can also give feedback in the general channel if you're interested in that too. All right, so with all that out of the way, here's what we're going to do. I want to talk about what SQL Server execution plans are. Some of you might already know, some of you might not, and I want to tell you why they're probably the most important and first step you can take when you're trying to make your SQL run better. Then I want to talk about what is the process of SQL Server creating an execution plan, and how do you view them, and how do you read them. And then finally, I want to spend a lot of time just talking about some common plan operators and what they mean, and why they might be influencing the performance you see with your queries. Then with any time left, I have some examples of when query plans go bad. So if you like looking at like bad query plan porn, that's a good place to start. So that's what we're going to do in this session today. So all the stuff I'm going to be working with today, I have a local instance of SQL Server 2017 installed on my laptop. And I'm using two publicly available data sets. The first one is AdventureWorks, Microsoft's tried and true demo database. You can grab that from the link below. And then I also have a copy of the Stack Overflow 2017 data. They make kind of anonymized data available, and it really works well when you want to see queries kind of fail at scale. So it's a good data set to work with as well. So if you're sitting in here and you're thinking, man, another SQL Server-centric based presentation. Does this apply to me because I don't use SQL Server? And the answer is sort of. It doesn't really matter what kind of database system you use. You are going to run into some query plan behavior no matter what you use. So if you're using MySQL or Postgres or even Oracle, there is some form of a plan that gets generated. Now, the operators don't necessarily match one for one, but the type of stuff you can learn by reading an execution plan applies to pretty much every relational database system, and even some that aren't. There's even functionality to get query plans in things like Hive, if you're working on HDFS. All of that stuff exists. It's also called explain query a lot of places. And there's different tools depending on what you're working with to view those plans. But again, today we're going to be focused primarily on Microsoft SQL Server. Doesn't matter if it's in the cloud or on premises either. Okay, so what is a SQL Server execution plan? Here's a nightmare scenario. You write a query, and you think, this isn't going to return a lot of data. It should probably run really fast. So you execute that query, your application hits that query, and it takes a minute. Your app probably times out, you're having a bad day, or maybe you had queries that were running really fast and now they're not running fast. What's going on? Well, see, what happens is when you submit a query to Microsoft SQL Server, there's actually a process that goes on behind the scenes that you're not even usually aware of generating a query plan. And a query plan is a set of instructions, a set of logical steps that the storage and data engine are going to execute to go and get your data and present it in the way you want. Here's how it works. So if you submit a simple query, the first thing that happens is your query gets parsed. Is my query syntactically correct? Did I type select instead of select because that R key is awful close to the E? Can't tell you how many times I've done that. Am I missing a from statement? Did I reference a reserved word that is missing some other syntax? Does it pass the smell test of a good syntactically correct SQL statement? If it does, then your query is passed on to what's called the algebraizer. The algebraizer takes your query and kind of separates out the T-SQL reserved words and ties the things you're trying to query to physical objects in your database, whether they're views, tables, functions, stored procedures, whatever. That stuff all gets sorted out. It also figures out if you're trying to do any type of aggregate information, if you're doing any group bys or summing. That type of stuff is also realized in the algebraizer. Once that step gets done, your query, all that information out of the algebraizer gets passed over to what's called the query optimizer, and this is where plans are born. Okay? SQL Server takes the output of the algebraizer and figures out what kind of query plan do I need to come up with. In a lot of cases, it'll come up with one plan. If you're trying to, say, insert some data or update some data, there's only so many ways you can do that. But if you write a complex select statement with a couple joins in it, SQL Server not only will generate one plan that gets used, it actually generates multiple plans. And the plan it ends up picking to run is done through a process called cost-based optimization. Each query gets assigned a cost under the covers. SQL Server looks at the aggregate costs, and those costs are made up of things of like expected CPU usage, expected memory usage, expected I/O that has to occur. SQL Server tries to find the cheapest plan that it generated, and that's the one that gets used. Once that happens, your plan then gets cached. There is a dedicated memory area in SQL Server that's responsible for maintaining all of those cache query plans because every time you execute a query, it has to go through all those steps to compile your query plan. Well, caching is usually good. So what SQL Server does is it says, I've already seen this query. I'm going to take this plan and I'm going to cache it. So if I see this query again, I don't have to waste that overhead, even as small as it is, to continue to recompile that query every time. Once your query gets cached, then the plan is handed over to the storage engine of SQL Server, and then the steps start to get executed. That's where you have disk thrashing, CPU burning, memory filling up, all the bad stuff that everybody loves to blame on the database. So that's kind of the process of how query plans get generated. And the thing is, they are so vital to how SQL Server logically gets your data and hands it back to you that if you come to me as a DBA and say my query's slow, I'm going to ask you for the plan. If you don't know what a query plan is, I'm going to say, just send me the query. And then I'm going to look at the query plan and try to figure out what's going on. Oh, and the other thing is, before I move on, is that it is possible to influence the plan that gets generated by SQL Server. Now, in my 15-plus years of working with the data engine, I think I have successfully outsmarted it twice. It's not something you generally want to do. It might help you get past a specific hurdle you're having with your query right now, but it can come back to bite you in the long run. And we'll see some query hints later on. So there's two types of execution plans that you can view in SQL Server. The first is what's known as an estimated plan. When you ask for an estimated plan, SQL Server does all of those steps up to actually running your query. So it will parse, algebraize, and optimize and select a plan. It won't cache anything because no query's been run yet, but it's going to hand back to you the expected plan that it is going to use to run your query. Now that has some advantages. Let's say you have a 5-minute query that you want to tune. If you're tuning iteratively, that means that you would have to basically wait 5 minutes in between each execution until you figure out what's going on. Realizing that that's not always best case, and I've seen some queries that are well over 5 minutes, not an indictment of anybody in the room, by the way. But if you don't want to wait for your queries to continue to run for 5 minutes, you can grab the estimated plan. The downside to using just estimated plans, though, is that it is just that. It's an estimate. SQL Server may tell you, hey, I think I'm going to return 270-some rows, but that might not be what gets returned, right? Because when SQL Server comes up with the optimized plan for you, it has to use some knowledge about what's in your tables, like things like column and row statistics, about the distribution of your data, any indexes that exist. It's going to estimate what it's going to do. You won't actually know what happens unless you look at an actual plan. And an actual plan contains everything that the estimated plan has, with one big downside. Your query has to run. If your query finishes successfully, in addition to viewing the estimated plan, you also get to look at all of the actual row counts, memory usage, CPU usage, disk usage that occurred. And what's interesting is that if you see big differences between estimated and actual plans, that's usually flavor country for performance tuning, because that means that you have something obviously going on with your query or your underlying data that needs fixed or tuned. Oh, and the other thing is, I said that plans can be cached. Your DBA, and depending on the rights that you have in non-production environments, because we never give everybody access for in production, is you can pull plans out of the cache and see what they are. And by the way, those plans stay in the cache for an indefinite amount of time. There are events that cause query plans to come out of that cache and need recompiled again. The two main ones that kind of come to my mind are that there's only so much memory reserved for the plan cache. So as new queries come in, if it hasn't seen that query for a while, it'll kick it out of the cache and then it'll recompile again. Or if your DBA restarts a server, or a server crashes, or there are commands you can execute to kick plans out of the cache as well. If you have a very, very busy system, your plans may not live very long if you're constantly seeing a bunch of different ad hoc queries. So having said all that, let's actually look at a query execution plan. Up here on the screen, I've got a sample query. It's just selecting some columns, and it's got a good old-fashioned inner join. There's no predicates, there's no order by, no fancy sorts, nothing like that. No fancy aggregate functions or anything. Let's take a look at what we're going to see here. Now, if I'm working in SQL Server Management Studio, there's one of two buttons I can click to view this plan. The button on the left is the toggle switch for viewing the actual plan. If you click that guy and then execute your query, you will see an execution plan when it finishes. The button on the right with the little speech bubble is the graphical representation of you asking for a query plan, is what I was told. I don't know. But if you click that, you will get a query plan generated and the estimated plan generated for you and shown on the screen. Now, in both cases, this is what a plan for this query looks like. Now, how do we read this thing? Well, we read it from top to bottom, right to left. These are the logical steps that SQL Server is going to take to make this query work. So at the very top there, we can see that we have an operator that says a clustered index scan. Then underneath that, we see a clustered index seek. Those two steps will be executed, and they both have to finish before the nested loops, which controls our inner join, runs. Now, the other thing I want to call your attention to here is that underneath each one of these operators is a cost expressed as a percentage. The reason for that is remember that these execution plans have a cost. Brent Ozar calls them query bucks. I mean, that's what I like to call them too. But they actually have no real-world bearing on anything. That number is completely meaningless. Once upon a time, here's a bit of trivia. Once upon a time, it reflected the amount of compute power that some employee's desk at Microsoft had a Dell server running under. That's what that number represented. Today, it means nothing. But the plan that was generated had the lowest of whatever that number means. So the cost expressed as a percentage here, which, by the way, if you're really quick at math, and I'm not, that adds up to 101% because, rounding. But those costs are the relative cost of each step in the total query. So you can very quickly bore in on where your expensive operations are in your query. Now, I got to tell you, if the most expensive operation you have in a query plan is an index seek, you're probably having a good day. If you've ever done this kind of tuning at all, that's actually a good thing to have. But when you have a big multi-step query and you have one step that is taking up more than 50% of your query, that might be a place to look and see, hey, maybe I need to do some tuning. So that's why it's good to look at this stuff and understand what's going on. So having said that then, let's go ahead and take a look at some common query plan operators and what they mean. The first thing I want to talk about are scans versus seeks when you're getting data back from the server. Then I want to talk about index scans and seeks and what the difference there is. We're also going to see some things like row lookups. We're going to see why sorting is really expensive in SQL Server. Then we'll look at some different join types, because these are the most common operators you'll see when you're interacting with SQL Server. So this is the part where we switch over to the demo. And hopefully I don't have to type anything, because you're never supposed to type in demos. And did I lose it? Uh-oh. Tech problems, yum. There we go. Come back to me. There we go. Not sure what happened there. All right, so you guys can see that okay, yes? Bigger, smaller, good in the back? Thumbs up in the back. All right, cool. Audience participation part done. All right, so here's what we're going to do. I'm going to run some queries here. And I'm going to run 2 queries at the same time. It's the first 2 ones at the list here with my favorite thing in the whole world to see is a DBA, select star. If you don't learn anything today, it's A, follow dog rates on Twitter, B, select star is bad. Those are the 2 things I want you to learn today. All right? So what we're going to do is we're going to select these 2 things and we're going to run them. Now what I'm going to do is up here in the upper corner of my screen, I'm going to include the actual execution plan. So I'm going to toggle that on. All right? So now when I run this, I get results at the bottom. So I have 2 result sets at the bottom, but I also have this tab that says execution plan. So here are my 2 execution plans for those 2 queries. Now there's a couple things I want to call your attention to here. Number 1, each one of those operators has a scan function in them, and each one takes up 100% of their total cost. There's only one operator, so it makes sense that we have 100% of the total cost in those operations. They both say scan, and they both have a little gray arrow that shows you how data is flowing between those different operators. So the difference you have to ask yourself is, well, okay, it says there that the query cost relative to the batch is 50%, and the other one's 50%. Does that mean the cost of both of these queries are the same? It absolutely does. The reason for that is those tables are identical except for one different thing. So if I put my mouse over this first operator, the select statement, we can view the cost of this query. It's expressed as estimated subtree cost. That is the query bucks that this query costs for the server. Okay? And we can see that the total cached plan size, it takes up 32 kilobytes of memory to cache this particular query. And it says the estimated number of rows returned is 505. How many rows did it actually return? Well, if we put our mouse over this little arrow right here, we can see how many rows flowed between the 2 operations. So actual number of rows, 505. That's the number of rows that flowed back to the user, to our last step in the plan, or the service, or the application, or whatever. Number of rows read, that's how many things were read off of disk to get you that data back. Now, why would those numbers ever be different? Well, if you're doing any kind of filtering, it may have to read more rows than it returns you. That sounds awfully inefficient, Drew, he said, sarcastically. So we want to try to avoid ever seeing those numbers differentiate too much, right? Then you see estimated number of rows. And here's one of the differences between estimated and actual plans. If I ran this estimated query and it said 498, but I got back 505, that's because SQL Server was doing something behind the scenes to try to figure out how many rows to return, but it didn't really match real-world stuff. And that's perfectly normal. And we'll see more examples of that in a little bit. Where you can have a problem, though, is when that number starts to get more and more further apart, then you can start to run into some performance issues as well. And there's some other data in there, too, that's pretty good to look at, like the estimated row size to return, stuff that can impact how much memory you need, stuff like that, estimated data size, all kinds of cool information. So the question then is, these queries appear to be the same. They're both doing what's called a scan operation. Okay? What is a scan? Well, anytime you see the word scan in an execution plan, that means that it's reading every row in a table. Right? The difference between these 2 operations is the top query is using a clustered index scan. Well, what is a clustered index scan? All that means is the table that it's reading all the rows from has a clustered index on it. Not necessarily a primary key. There's some differences between a primary key and a clustered index. I think a lot of us just create primary keys and get the clustered index as a result. But what that means is that table has a clustered index on it. When a table has a clustered index on it on SQL Server, that enforces the order that the data is stored on disk. So it's basically reading things sequentially in order of the defined clustered index. Make sense? On the other hand, my second query is just a good old-fashioned table scan. That's because it's reading from a table that doesn't have a clustered index. It's reading from a table that is basically called a heap. Just keep throwing data on it, right? How does this impact you if you see this type of behavior? From a read perspective, that means that you probably don't have a where clause or a really inefficient where clause, number one. So you're probably reading more data than you actually intend to read. The other thing is, it doesn't really impact you so much in reading. Where these type of scans can come back to hurt you is when you're actually changing or inserting data. It's really, really cheap, query-wise, to heap more data, it's a callback, heap more data onto the product archive table because there's no clustered index. All data always goes onto the end of the table. Whereas when you have a table that has a clustered index, it's more expensive to insert data in the middle of it because it has to reorder that data on disk every time you put new data in. From a read perspective, both of these are the same. There's the same amount of data in both tables. It has to read every row and return every row. That's why you see the word scan. That's the key word there. Now, sometimes, though, queries that you think are going to come out to be scans aren't necessarily scans. Let's take a look at another example here. I'm going to select star from sales.customer. It's a whole different table this time, right? Now, you think you're going to see, well, I don't have a predicate, and I'm doing select star, which is Drew's favorite, so I'm probably going to see another table scan, right? Or a clustered index scan, hopefully. So there's my results, and when I look at the execution plan of this one, wait a minute. Well, I certainly didn't do anything that would require a computing scalar on these type of selects, right? What's going on here? Well, remember that SQL Server has to figure things out sometimes when you select data. In this particular case, we have a computed column in our table. So what SQL Server is telling you is it's not just enough to read from disk sometimes. There could be other steps along the way. Even though all you're doing is technically retrieving data, when you have things like encrypted text or computed columns or anything that aren't persisted, this stuff has to be calculated over and over again. If I were to pull up that table definition, you would see that column actually is comprised of two functions, a good old-fashioned isNull and a user-defined function. And that's represented from both of those steps. And we can see that still my read is the most expensive part of this operation, but then we have the compute scalars eating up 2% of the cost as well. So is that inefficient? In this particular query, no, because it's still more expensive for me to read the data off disk. But if I did have a query where I was seeing a lot of compute scalars over and over again with my selects, I may want to think about basically materializing those columns instead of doing computed ones. So not all selects are the same. That's why it's never a good idea to just assume when you're doing a select star from a table with no predicate that all you're really waiting on is the disk. That's not a safe assumption. It could be related to CPU. So if I put my mouse over this, we can see the estimated cost of each one of these operations, right? So I can see here that the estimated CPU cost is, 0.001982 query bucks or whatever we're calling it, okay? So there you go. All of these things have some really cool information on them as well. Now, those are scans. I'm reading every row from the table. I hate scans. Scans are really inefficient. They can be slow. You're probably selecting more data than you need. So if you're a good SQL dev, what do? You add a where clause. Where clauses make things really interesting, right? Because maybe we can get away from table scans. Here's what we're going to do next. We're going to switch tables for a minute. We're going to work with the person.person table. Now, the person.person table is a really good table to run some examples against. Just to give you an idea of what this table looks like, here it is. I've got a bunch of different columns on it. It has a primary key. It's a clustered key. So we know that my data is going to be stored on disk in order of business entity ID. It's just a good old-fashioned integer column. Basically, the data is stored on disk in that order. With me so far? There's also some indexes on this table. The one index that I want to call your attention to is that there's a pre-created index on this table that has last name, first name, and middle name in it. That's going to be important in a minute. Okay? So those are the things that exist on this table. So that can lead to some pretty interesting behavior when we start to query this table. The first thing I want to do is I'm going to do select star from person.person, where the person type is EM for employee. Now, what do we know? We know that that column is not indexed, first of all. And we know that we're doing select star, so I need every row from the table. What do you think a plan like that looks like? Do you think it's very different from what we've seen so far? No. Remember what SQL Server does when you submit a query. Even though we used a where clause, it still had to scan every row in the table. Why? Well, in order for it to find out what columns have EM on it, what does it have to do? Read every row from the table. That's pretty inefficient, right? Which is why sometimes you'll see that helpful green text that says, hey, buddy, I could use an index. But check this out. If I put my mouse over this arrow right here, this is where we start to see the estimated versus the actual behavior start to differ. We can see that the actual number of rows, the number of rows that got passed back to the select statement was only 273. So there's 273 rows in that table that match that criteria. How many rows did it need to read to get there? Almost 20,000. I/O can be very expensive in terms of a SQL query. Look at that estimated number of rows. 297.256. Well, you can't be a little bit pregnant, and you can't get a little bit of a row, right? So what does that number mean? Well, remember that SQL Server has statistics about your data. There's a giant histogram of how data is stored in your database. When SQL Server generated this plan, it looked at the statistical distribution of the data for that column and decided that there's going to be about 298 or 297 rows returned. It was pretty close. Okay, that's not a huge difference there, but for that little of data, it's actually a bigger gulf than it looks like. So it still had to read everything from a table, a scan, yucky, boo. How can we see the difference between scans and when we get an index? Well, one good example of that is, what if we select everything from that same table, but this time we select something using the clustered index? I'm just going to select what essentially is the first row from that table using the key. If I do that, look at what I get now. Now I have what's known as a clustered index seek. I don't see the keyword scan anymore. The difference between a scan and a seek is basically not reading the entire table. I'm able to read one or a range of data from a given index, which is way more efficient than trying to read the entire table. So let's take a look at this at the metadata coming back from this plan real quick. If I put my mouse over this, it nails it. It knows that I only need one row because there's only one unique value of that in the table. It's a much more efficient plan. Now, obviously, it's pretty limited. We're only selecting one row. But now that we've seen what a seek is, let's see it kind of see it grow up a little bit. I'm going to change my query again. This time, I'm going to select first name and last name from person.person, and I'm going to filter it by last name. So we know that this table has an index on it, and we know that last name is a part of it. So what do you think we're going to see when we run this? A much better plan, actually. Now we're seeing an index seek. Why is it not a clustered index seek or a table seek? Well, it's because we have an index. Now, if you've ever spent time creating indexes in SQL Server, you may already know this, but what happens is when you create an index, it actually creates a side-by-side copy of your data. Now, if a table has a clustered index on it, that enforces how the data is stored on disk for the table itself. When you create an index and it creates a side-by-side copy of your data, you're actually getting the same data that's in your table with the same values, just sorted in a different way. So in this particular example, it knows, because I'm filtering by last name, that it can immediately go to my index and get what it needs, and only my index. And it's pretty spot on with its estimated and its actual. Because there's not that many rows in the table, it can have a really nice statistical histogram of my data and know exactly where to go. So that's the advantages of using indexes, and we're now out of scan land and into seek land. Okay. I've stood up here and I've said words like good, or better, or bad, or worse, or not so great. Those are qualitative. I always get that wrong. Those are qualitative words, right? How do we actually put into numbers how much better these queries are than the other? Well, you have some tools at your disposal with SQL Server to help you measure your query performance other than just query plans. One of those is a session-level statement you can run called set statistics IO on. When you run this, you're basically telling SQL Server, for the rest of my session, in addition to giving me results, give me data on how much I/O you generated for a given query. Okay? As long as this stays on, and as long as my session is active, I will get that information. So let's do this. Let's go back and revisit some queries real quick. The first one I want to run is select star from person.person where person type equals EM. We know that that was a scan, right? Same plan as I've seen before, but check this out. Table person, scan count 1, logical reads 3,820. There's our baseline. If I want to read everything from person.person, that's about as many logical reads as I'm going to get. What does that number correspond to? That's the number of data pages that SQL Server had to read to return this query. I/O can be expensive. It's a number of 8K pages that SQL Server had to read. Now compare that to one of our other queries. Let's go down here and do select star from person.person where last name equals Smith. Drew, it's going to be a Sikh. It's going to be so much better, right? I'm just going to go over here and look at my index Sikh and, uh-oh. What's going on here? Well, we've got a problem. As the founder of the church of not using select star, this is what happens when you use select star against stuff that has indexes on it. It's true, I did get an index Sikh up there, right? But look at where the total cost of my query is being spent. In an operation that says key lookup. What did I do different in this query? I used select star. Remember what my index has. My index only has last name, first name, and middle name. So when you do something like select star, SQL Server, when it came up with this plan, said, I can get pretty close on the rows I need to get without having to read everything, but I do need to go back to the table to get the values that aren't part of my index. That's what that key lookup means. There are values you're selecting that are not in that index that it's using to filter your data, so SQL Server has to go back and get it. Now, we certainly didn't write an inner join here, but SQL Server under the covers needs to rejoin those two operators together, and we have a pretty inefficient query. That's why select star can be bad sometimes. Actually, it can be bad pretty much all the time. Compare that to then, okay, so here's the data we got out of that. So now we only had to do 328 logical reads, about a factor of 10 improvement from our I/O perspective. It's not bad, a factor of 10, it's a pretty good improvement, right? So is that good? Well, it's better, right? It's better than reading every row from the table. Now compare that to doing something like a straight up index seek. Let's fix our query to do this. We're going to go back and select only first name and last name, and we're going to filter by last name. We know that this plan has just a seek operation, and our total logical reads was only 4. So we went from 3,820 to 4 with an index. That's why this stuff matters. Now again, on my Dell laptop with a local SSD, that may not seem like a lot, but when you have older SANs or large, very busy systems, this stuff can add up really quickly. So understanding query plans and being able to pull this type of intelligence back can be really, really important for trying to troubleshoot slow-running queries. Now, one more thing I want to show you before we move on. I'm going to change this query up. Instead of filtering by last name, I'm going to filter by first name instead. Let's see what that looks like. Do you think I'm going to get an index seek on this one? No. I'm back to a scan, but look what it's scanning. It's scanning my index. Because I selected things just from the index that I'm trying to pull back, it doesn't need to go to the table. It just needs to go and read every row from the index. And because the index was structured in such a way that it only has 3 columns, it's still 136 reads. But it's not as expensive as reading the whole table, is it? So there's an actual index scan. Just because you have an index and it gets used doesn't automatically mean it's always going to be a seek. It could still be a scan. Cool so far? All right, so having said all that then, let's go ahead and turn our statistics I/O off for now. Just wanted to show you that. Now we're going to talk about some other performance killers that you can see in query plans. And my favorite one to show off is the good old-fashioned order by. So let's select star from person.person, and let's order by person type. Now, I actually took a little bit longer to run, even on my laptop. Here's my query plan. Well, I'm doing a select star, not doing any kind of filtering, so I'm back in scan land, population us. 68% of the total cost of my query being spent reading that data off of disk. Then I have a sort operation because I'm ordering by person type. Now my data is stored on disk right now because I'm reading from the table by my clustered index key. So it has to reorder that data to bring it all back to me. That sort operation represents that. So let's take a look at the cost of this query real quick. Total cost, 4.167 query bucks. Again, no real bearing on that number in the real world. That's just how SQL Server costed this query out. Then we've got a clustered index scan. So it's reading every row, and then it's sorting every row. Okay? Here's the thing about sorts, guys. They're bad for a lot of reasons in SQL Server. It's a very expensive operation. One, it eats up a lot of CPU to reorder your data. The other thing is that if you have a very, very, very large data set that you are ordering by, there's a chance that it has to write some of that data to tempdb. That's called a tempdb spill. So now you have the law of unintended I/O on top of all that CPU. So sorts can be very, very expensive. And we can see that even though reading all the data is still technically more expensive here, the total cost of the sort is about 1/4 of the total cost of the query, give or take. So let's change this up a little bit. How can I get rid of this sort and make this query more efficient? Well, what if we go back and let's use our index? Let's revisit this query again. Select first name and last name from person.person, order by first name. So I'm selecting columns that are part of an index. So guess what? I have an index scan, which is cheaper than a table scan, as we've seen, correct? But now the sort is by far and away the most expensive part of my query. My total query cost has dropped to 1.4, so I've seen a cheaper query be produced, but my sort is pretty much all of it. So wouldn't it be great if I could speed this query up by eliminating this sort? How would I do that? Well, we've already seen the answer to that. What if we use an index? Remember that when we create the index, we specify the order of the columns in the index, and that determines how the data is stored on disk. So if we have an index and we use that to sort our data on disk, we don't need to do it in a query. It just comes off the disk sequentially and gets returned to us. We can save that step. So if I run this, now my sort is completely gone because I'm leveraging an index. Why do I tell you this? Well, number one, it's going to be faster almost 99 out of 100 times to do your sorting in code. It's just going to be. Because SQL Server can do sorts, but it's pretty inefficient. The other thing is if you find yourself consistently sorting data over and over and over again, it's a really good candidate to create an index so your data is ordered that way so you can save that step when you're running your queries. Sorts, very, very expensive. So anytime you see that, that's what's going on. We're going to see more sorts in a minute where we didn't tell it to sort, but it gets sorted anyway. So now I want to talk about joins. Joins can be very expensive in SQL Server because think about what you're doing. You're taking a bunch of data, you're getting it back, and you need to match it up with other data. Typically, you'll see 3 types of join operations in SQL Server. You'll see merge join, hash join, and nested loop join. Is there one sort that is better than the other? No. Every sort in SQL Server is designed for a particular use case. Where you run into problems, though, is when you have a sort that is used when a better sort could have been used instead. And a lot of times, in order to get the sort performance that you want, you need to first understand what's happening with your data. So maybe you can refactor your code or your indexes to support these large join operations. So here's 3 join examples. All right, in my first query here, I'm basically selecting from the person table, and I'm joining the email address. Now, I'm joining on email address to the clustered index on both tables. Okay? That's the key here. Now, I'm filtering on last name Smith. What does my query plan look like for that? Well, it looks like this. The first thing I'm doing is I'm doing an index seek on person.person because I have an index and I'm filtering by last name. What's that sort doing there? I didn't tell it to order this data. Why do I have a sort operation? take one step to the left, and you'll see that SQL Server decided to use a merge join for this plan. What is a merge join? If you can imagine your data being shuffled like a deck of cards, that's kind of what a merge join is. It's basically taking your data and sorting it, or merging it all together kind of on top of each other. And the only way that works is if both sides of the join are sorted in the same order. Because it had to go read every row from email address, the data came off of disk in order of the clustered index key. It came out of our index by last name. So what SQL Server had to do is sort that data. Now both sides of that join are sorted in the same way, and I got a merge join. That's actually a good plan. And remember that SQL Server probably evaluated doing this same thing with a different type of join. This was the cheapest plan that it came up with. This is where we really start to see really very, very wildly different query plans. So a merge join is very, very efficient. It's not a very expensive operation. In fact, it takes more to get our data off of disk than it actually does to do our merge join. Total cost of the query, 0.27. This thing's 18% of that total cost. That's actually pretty good. That's what a merge join is. Hash match joins on the other example. Who here has ever written a hashing algorithm? A few of you, I would assume, or uses hashing on a regular basis. In this particular example, here's the code for this query. I'm joining the two tables, and I'm looking for a thing between a range of dates, selecting a lot of different columns from the table. Now, in this particular case, SQL Server decided to use what's called a hash match join. And a hash match join is basically SQL Server building a table of hashes for your rows on both sides and then joining them up. You will usually see hash joins when you have very large sets of data being joined together. It's actually pretty efficient for very large data sets. Where it can be inefficient is when you have one very large set of data on one side of the join and a smaller set on the other. Usually that's a candidate for the next type of join we're going to see, but it's not always the case. Hash matches basically use hash tables to join them up. Again, really pretty good for big joins. And then finally, we have nested loop joins. Now for this particular query, let's look at the code real quick. We're just basically doing one inner join here. We're still sorting by the business entity ID, which is the primary key column, but I'm selecting from the human resources table this time. So it did two clustered index seeks to get this data, because I selected data out of the table, right? Then it did a nested loop join. Nested loop joins are exactly what they sound like. You have one very small data set and a slightly larger data set on the other side, and it basically loops through them and joins them up one at a time. Kind of like a giant spool that's raveling up, right? That can be a very efficient join so long as one side of your join is really, really small. Joining a very, very tiny data set to a large data set can actually be really efficient with a nested loop join. So why go over this? Well, it's important to understand how those different join types work, because a lot of times, if joins are expensive in your queries, then probably SQL Server is deciding that this is the best plan it could come up with given the circumstances. You can usually tune join behavior by looking at things like your indexes or how you're getting the data out of your tables in steps prior to that. All right, so I've got about 15 minutes left, I think, or am I done? No, I got 15, right? All right, cool. So now that we've gone over some common query plan operators, it's time to start seeing what happens when query plans go bad. So I don't know if you know this, but sometimes computers make bad decisions. SQL Server is no different. Sometimes SQL Server will generate a plan that doesn't make any sense. Or sometimes it'll generate one plan one way and the same plan for the same query a different way. So now I want to show you a couple different examples of when this stuff can kind of go sideways on us. And the first one I want to show you is this thing called parameter sniffing. Who here has heard of this? Parameter sniffing is actually a working as intended feature. Kind of goes back to why we cache. Remember what happens when we generate a query plan? Our plan gets cached. That means that if we ever see that query over and over again, SQL Server doesn't have to waste time making a plan every time. Pretty efficient. The problem is when you have things like parameterized queries, sometimes the data that was used to generate the plan was off one set of statistics. What happens if you pass in a different value and it tries to use the same plan? It may not perform the way you expect. That's one of those, hey, it used to run fast, now it doesn't type scenarios. How do we diagnose this? Well, here's what I've got. Let's take a look at these 3 queries right here. I'm going to basically select from person.address, and I'm going to do it by a column called state province ID, which is basically an integer representation of a state. Let's go ahead and run that. Let's take a look at these plans real quick. The first 2 plans look pretty similar. SQL Server said the best way for me to get this data is to go do an index seek on that index, and then go back to the main table, find the missing values, and join them together with a nested loop. Check out the total cost of the batch. The first one was 22% of the total batch because it returned more rows than the second one. It used the same plan, but check this out. Actual number of rows, 16 versus 16, and then 1 versus 1. So that's why, even though they're the same plan, one query was cheaper than the other. Okay? But when I select from the same table down here, I get a slightly different plan. And it won't let me go any further. Let me just do this one. I get a way different plan than I saw before. Now SQL Server said, hey, buddy, the best way for me to get you this data is just to do a table scan. There's the difference in the plans. Where this gets to be a problem is when we start using things like stored procedures. Let's say I wanted to write a stored procedure that ran this same query. I'm going to go ahead and create a stored procedure now. And I'm going to call it get addresses for a specific state. So select the address information from address where I pass it in a state province ID. Now, I'm going to execute it for value number 9. So I'm going to run that for what is my big boy, what's going to put it into a table scan, right? So what happens when I run this? SQL Server is going to generate a query plan. Here's what's in my cache, table scan. That might be really efficient for this value, but watch what happens now when I pass in 55. I had to scan the whole table. Why? Why am I seeing this behavior? Well, because I have a parameterized query, SQL Server's already seen this query before. I got a cache plan for the table scan. Is that good? Well, maybe it runs really fast for certain values and really slow for the others. This is parameter sniffing. How do we deal with this? Well, there's a couple of different ways we can handle this. The first is the nuclear option with recompile. If you create a stored procedure with recompile, you are telling SQL Server every time you run this stored procedure, recompile it. Generate a new plan every time I run this. If this is a stored procedure that runs a couple times a day, this might be an option. But what happens if this is like the core business, like stored procedure on your very busy OLTP system? You're going to spend time in CPU cycles generating query plans every time the stored procedure gets called. That's not great. It works if we do that. So let's alter this procedure with recompile. And now, anytime I run this stored procedure, I get the most optimal plan based on the data that was provided. So recompile can fix that issue, but it may not fix it in the way you think. Yes, you're going to get a better query plan, but now you have more plan recompiles. That might make your DBA sad. Just FYI. So if we can't use recompile, then what can we do? Well, there's other ways we can influence query plans. And this is one of those things where I said you maybe shouldn't outsmart the optimizer. If we know that we have a very heavy data skew in our data set, we can tell the optimizer what to do with our plan when it's first generated. Check out this next alter procedure statement. I got rid of my recompile, but now I'm giving it this statement that says option. I'm telling it that if you do recompile it as if I had passed you value 55. So if I run this, and then run my stored procedures, I get that more efficient plan. Now, how expensive is this one? 0.05 versus 1 point whatever it was. They're actually the same value for each. We've influenced how SQL Server generates these plans. This is a very clever way to solve parameter sniffing, but it requires you to know what's going on with your data. So there's a trade-off there. If you know you have data skewed to a particular side of the spectrum, and the only way you know that is by if you have people consistently looking at your data, this won't work. You will eventually run into the same problem you were having in the first place, where you have plans generated for values, like maybe 55 is the biggest value in my table right now, but what if that changes? Now I'm back right where I started and I got to alter this. But those are two different ways you can deal with parameter sniffing. All right, the last thing I want to show you, just because it's important to me, and I won't forgive myself if I don't get to it, is the use of cursors. Not a fan. Not a fan. Who here uses cursors? I'm not going to judge. I'm judging. I'm sorry. But I don't like using cursors. Okay? Why don't you like cursors, Drew? Well, they're very inefficient ways to work with your data. Okay? If you're doing this in an OLTP system, you're basically making SQL Server do extra work for batch type operations. Okay? And my goal as a DBA is to try to kill cursors with a fire. One of my DBA mentors once told me, when I asked him if I should use cursors, he said, cursors absolutely have a time and place in SQL Server, but you're probably not smart enough to know when they are. And he was right. And I still don't necessarily know, but I can identify bad query use of cursors when I see it. And the way I can see that is through using execution plans. So let's do this. I'm going to declare a cursor. All right? I'm going to do this in a transaction. So let's say I have a situation where I need to modify a bunch of data for a bunch of customers. Right? Ooh, I have to fix apps that were blurry. Thanks, Windows. Let's say I need to basically loop through. Here's a common scenario. I need to insert a value into a table, and then I need to take the value that I just inserted and then find something about that value I just inserted and fix it. Typical cursor use case. Right? Maybe I want to use my good old-fashioned, scope identity to get the value I just inserted. So let's go ahead and run this in a cursor and see what happens. So I have this big transaction here, right? My query's still executing, my query's still executing. Look what's happening. Plan after plan after plan after plan after plan, because it's going to keep running, right? This is very inefficient. I'm 12 seconds into this fix. Drew, is there a better way where I don't have to use cursors? There absolutely is. A lot of times people use cursors when they need to take the value that they just got and do something with it. One way you can get around that is to use what's called an output statement. Who here has ever used output before? A couple of you? Cool. I like when the IGS people raise their hands. So output basically does the same thing as scope identity. You can capture what was the output of another query and then use that to build a temp table of values, then pull those values back and do work. We're going to do a set-based operation instead of a iterative one. The difference here is I can do this all in one query. It still takes, I don't know, 5, 6 seconds maybe? Yeah, 6 seconds. I get a pretty hellacious plan for every step, but guess what? It's a set-based operation. 6 seconds versus, I don't know how long that cursor would have run. I'd never actually let it run all the way. We might be in here well past lunch if we do that. But that's one way you can eliminate cursor use and get away from using scope identity to fix problems. That's why cursors are bad, the end. Okay, before we wrap though, there's a couple examples of execution plans gone wild. A couple other things I want to mention. And I don't know what the clicker, oh well. A couple other things I want to mention real quick. There's other cool stuff you can do with query plans as well. One of the cool things that was released in recent versions of SQL Server is the idea of this thing called a plan store. The plan store is kind of a database within a database that can keep track of execution plans over time. And your DBA or anybody that has access to see it can basically see a regression of a stored procedure. And if a plan was particularly useful for a stored procedure, you can basically tell SQL Server, hey, when you see that stored procedure, use this older plan. It's basically another way to fix parameter sniffing. It's in some of the newer editions of SQL Server. Look, I get it. Some of you probably still have SQL 2000 and 2005. Again, no judging. I know what it takes to upgrade. It happens. The plan store is really good for that. The other thing I like to talk about is if you find yourself looking at plans all day, consider downloading SQL 1. It's no longer SQL Sentry. It's now known as Sentry 1. Sentry 1 has a free tool called Plan Explorer. It makes working with really large query plans much better than you can get in Management Studio. Really good syntax highlighting and really good information that gets presented kind of in a grid. It's a lot easier to work with. If you want to learn more about query plans, there are people who can talk about this stuff all day. The two people that I would refer you to is first Brent Ozar, and the other one is Grant Fritchie. Both of them are published authors on this subject. I highly recommend you check them out. There's the websites for both. Underneath Brent's link, there is a website called Paste the Plan. It's basically Stack Overflow for query plans. The way it works is you could take a query plan output from your machine, paste it into that website. It'll be anonymized, and people can comment on your plan and give you feedback on what you could do to make your plan better. You can kind of look at a hall of fame of like really hellacious queries out there too. It's pretty cool. It's all fancy web-based stuff. If you're local to Columbus, we have SQL Server resources that you can get as well. The first one is PASS. Used to stand for the Professional Association of SQL Server. Now it literally stands for nothing. It's just called PASS. It is a giant organization of data professionals, whether you're SQL Dev, SQL DBA, BI developer, whatever. You can join that organization. It's free. There's all kinds of events that go on all year. For example, we have chapter meetings in Columbus. We meet basically the second Thursday of every month, free to all, free food included. And then we also have a big day event here in Columbus every day called SQL Saturday. Maybe some of you have been to those. Again, free event. You can come out and learn from all sorts of people, maybe even me if you want to ever see me again. So hopefully I've imparted upon you why it's important that you look at SQL Server execution plans, some common plan operators, things you can do to make your query life a little bit easier. You get a little bit of insight as to what DBAs do all day when people say my query's slow. Maybe that makes you want to spend a little more time with your DBA, which I think is a win-win for everybody because DBAs are actually friendly, believe it or not. So you can check that out. So like I said, guys, if you want to learn more, you have questions for me, feel free to fire them off in the Slack. I'll be hanging outside Theater 27 here for the next little bit. You can come by, get a business card, say hey, tell me if I did good, tell me if I did bad. Would love to hear from you. I really hope you guys enjoy lunch, enjoy the rest of Star Trek. Thanks a lot for coming out. Yep.